Hello, I'm Chloe, and today I'm going to be talking about how we can reduce evolutionary volatility in collective systems by using social action. So I want to begin with a motivating example, and I'm going to jump back quickly to 2010. So in 2010, there was a $1 trillion stock market crash, and this happened in just 36 minutes, which is an astonishingly short amount of time. And part of the reason that this happened in the first place was that there were a number of automated trading agents that were making decisions based on the state of their environment. So an agent would make a decision which would change the environment for all of the other agents, and then another agent would make a decision and that would change the environment. And this led to a spiraling effect, and it led to the magnitude of the crash that we saw in 2010. So unintended interactions between entities can have a catastrophic effect, and you can see that in the diagram on the screen. So these automated trading agents were experiencing something called interference, and this is described as the interaction between entities in a shared environment. And this can be a purely human system, a purely technical system, or a combination of the two as well. And these trading agents experience interference from the indirect and the unknown interactions from the other trading agents within the system, because it changed their environment in ways that they didn't understand. And this meant that they couldn't act appropriately. And that led to the catastrophe that we saw in 2010. So an inability to understand the interactions with other systems in the environment can lead to volatility. And this is essentially where the fitness or the success of the system fluctuates because the agent or the system can't act appropriately, and it can't respond to changes within the environment. So ideally, we'd like to build systems that have less volatility in them, because that would mean that they're able to respond more appropriately to changes within their environment, to interactions with other entities within the system as well, even when they're unknown. So current methods to tackle interference look at what can be done when other systems in the environment are known, but this isn't always possible. Having complete and full information about the systems and other systems within it isn't always possible, and collective systems are usually designed with partial information. So trying to learn new things and trying to understand how to interact with other systems is always a difficult problem. But humans overcome interference all the time, and that's because we have evolved to act socially. We're able to perceive things about one another and use this knowledge to base our actions and our decisions. And we can also achieve a lot more collectively as a society than any of us would be able to do individually. And that's a component of collective systems as well. And at the moment, current systems are pretty goal-oriented. They're not very good at learning about other systems within their environment, and also the impact that the interactions with these other systems can have on their own success and their own performance. So in our work, we look at how we can look at sociology theory, because humans are so good at dealing with interference, and how we can use this sociology theory to build collective systems that can overcome these issues. So we in particular look at Max Weber's social action theory, and he puts forward 4 different types of social action that govern how we behave and how we act in society. The first one's called instrumental or goal-rational action, and this is where you perform an action because you think it's going to be the most effective way to achieve your goal. And this is where you choose the means of or the action specifically to achieve your goal. Value-rational action, on the other hand, is determined by the values or the beliefs that you hold. And this is where the value of performing the action carries meaning rather than the result of the action. So if you had the goal of going to the supermarket and buying a piece of fruit, if you valued buying fair trade products, that would change how you achieved your goal, and then that would carry meaning for you. Effective action then is in a response to an emotional state like anger or passion, and it's an irrational action that's hard to justify because you don't consider the consequences of the action when you perform it. So this will be like striking someone in a fit of rage, for example. Finally, traditional action is like a habit or a cultural custom, and you do something because you've always done it that way, and it's mindless or automatic or ritualistic. And this might be something like eating with a certain set of eating utensils, or it might be driving the same way to work every day. It might not necessarily be the most efficient way of getting to work, but you do it because that's just what you always do. So building evolving systems to meet goals that exist in shared worlds is no longer sufficient because they can experience interference. So in our work, we explore how traditional action can help these systems to achieve their goals despite interference. And to do that, we use our testbed, which is the river crossing dilemma. And this is a simple 19 by 19 2D grid world environment with a river of water running down the middle. And our agents' goals are pretty simple. What they have to do is they need to collect one of their allocated resources from either side of the river. But the difficulty here is that if they fall into the river, they're going to drown, so they need to find another way across. And to do that, they need to pick up stones and put them into the river to build a bridge. And to build a bridge, you need to put 2 stones in the same spot. To make this a little bit more difficult for our agents as well, the task is also gamified. So there's an increasing cost of placing stones in the river. And one important thing to note about this environment is that our agents have no knowledge about the other agents in their environment. They do not have the capacity to learn about them either. So cooperation and competition might emerge, but it can never be intended because the agents don't have that knowledge about the others within the environment. So how are our agents designed then? Well, very, very quickly, there are 2 different neural networks. There's a deliberative layer, which generates sub-goals. So it takes in the current agent state and the state of the environment, and then this decides what it wants to be attracted towards and what it wants to stay away from in the environment at that current time step. And our agents learn using neuroevolution. So we mutate the weights and adapt them over time over a number of generations in this deliberative layer. So the sub-goals from this layer are passed on to the reactive layer, and the agents can use that to hill climb towards certain objects in the environment that they want to be attracted towards. And there's a visualization of that in the bottom right-hand corner. So they can hill climb, choose the highest value until they reach the peak, which is their sub-goal. And the agents also have no prior knowledge of the task or the environment as well. How do we incorporate social action into our agents then? Well, goal rational action is what current systems express most of the time. And this is where we have a tournament of 3 agents and we replace the worst performer in that tournament with the offspring of the best 2. There's a 95% chance for it to inherit from one parent, and then obviously a 5% chance for single point crossover as well. Traditional action, however, there is a 90% chance for that goal rational offspring to be produced, and there is a 10% chance to replace the offspring with a traditional offspring. And this is calculated from the median weights across the population in that deliberative network. We also want to compare this approach to a widely used approach in evolutionary algorithms to increase population diversity, and this is called random immigrants. So we introduce random action as well to compare this to both goal rational action and traditional action. So with random action, instead of replacing it with a traditional agent, we replace the offspring with a set of random weights. So we generate a random solution and insert that into the population. So we want to compare our approach, our traditional action and goal rational action approach, and see whether it is statistically different and whether it's better and what the effects of these 2 approaches are. Because we also want to have a look at volatility, so how much the fitness fluctuates over time, we've defined 3 fitness metrics. We have the standard deviation over time, the cumulative absolute change in fitness over time, and also the count in change in fitness over time. So this last one is how many times the fitness actually changes, whereas the middle one is how much, what's the magnitude of those changes over time. So in our experiments, we firstly look at what happens when an agent evolves alone in this environment. And we evolve the agent for 500,000 generations. And we can see that from very early on, this agent is actually able to maintain its goal-achieving behavior. And this is from about 50,000 generations. So a goal-achieving behavior in this task is 0.7, because it has to incur that cost of building a bridge in order to achieve its goal. And the agent is able to maintain its behavior because it doesn't experience interference. So there's nothing else going on in the environment, and it can completely understand how to interact with the environment and achieve its goal. So when we change this then, when we change our agents from being in a single agent environment to a multi-agent environment after learning alone initially, we can see that actually there is a lot of volatility in that environment. So if we look at the top graph here, we can see that when there's 2 agents in the environment, the fitness fluctuates a lot, and any fitness below 0.7 is not achieving the goal. So for a good portion of this evolution, the agents can't actually achieve their goal. And this is because they're experiencing interference and they can't understand why their environment is changing around them. And because they can't learn about the other agents in the environment, that's adding to the difficulty of trying to navigate this and to achieve their goals. So because they experience this interference, the evolution is volatile. However, when we add traditional action into the mix, which is what you can see on the bottom, so we've repeated the same experiment, firstly with just goal rational action on the top, and then the second one is goal rational action with traditional action. We can see that traditional action actually reduces this volatility, so much so that the agents actually also are able to cooperate. So a fitness of 0.9 means that the agents are sharing the cost of building that bridge. So they're much better off for this. This result doesn't happen all the time. They don't always default to cooperation at the end, but this is a very interesting result and an emergent property from this particular run. And we can also see that with a little bit more further analysis, we can see that the fitness between the goal rational agents and the ones that use tradition is not statistically different. So to go into the analysis a little bit more, we've created some box plots to see what the volatility for each experiment appears as. And we can see that traditional action actually reduces the volatility significantly, and we've run statistical tests as well, which confirm this. We can see that random action also gives agents a higher fitness because we're injecting the population with more variation, but they're also more volatile because of this as well. So there's a trade-off here. The agents that use goal rational action and those that use traditional action don't have a statistically different fitness, but the ones that do use traditional action are statistically significantly less volatile than the ones that just use goal rational action. So there's a big benefit there. So what are the implications of this work then? Well, designing socio-technical systems that are collectives to be goal rational is no longer sufficient. And that's because when agents exist in a shared environment, they can experience interference. And if they don't understand the implications of the actions of others within the environment and the interactions with others, then this can lead to problems and a loss of performance as well. So systems in shared environments need to overcome experience, and traditional action can help to do that. So the main takeaway of this talk is that traditional action can complement goal rational action to reduce volatility in evolving socially situated agents. And that's it. Thank you very much for listening.